Well, it's Cliff Collins. I'm the developer of Jane. I have about 50 years experience, just about 48 or something like that. Software development experience. Started out on the IBM 360 at the University of Houston engineering department, Fortran, and gone through all the other languages, C, C Sharp, Java, JavaScript, C, COBOL, Fortran. Worked on all the machines from the IBM to the MDOS to the Cray to the CDC to the Honeywells to the Enovac, Wang, DEC, PDP 1170s, VAXes, the Unix boxes, Linux boxes, just about every piece of hardware and software. I've written compilers and device drivers and accounting systems and operating systems and editors and basically anything that is software related. My main expertise, I guess, was translation of binary structures. My main job was to translate people out of proprietary mapping systems. So there's about 40 mapping systems, and so I wrote for 25 years is to move people off of mapping systems that they were locked into because the vendors would not give them any way to extract their own information out of these systems. So I'd go in and I'd extract it for them, make sure that it was 100%, got all the attributes. Generally mapping is in 3 systems, which is your graphics, pure graphics, 2 and 3 dimensional. And then you have your attached databases if it's available, or if it a lot of these systems didn't have databases originally. And then finally your networks. So you have something like GPG and CableCAD that are connected. Anyway, so my job was to make sure that 100% of that information was moved from one system to another. And so this was every mapping system out there. And I worked mainly for utility companies, oil companies, government entities, telephone companies, basically the people. And I did about 100 of these systems. Anyway, that's me. And so about 10 years ago, I started Jane, which was, I was asked by eBay or interviewed by them to manage 200 people to write them a new software foundation. I didn't get the job, but it started me thinking, what could I actually write somebody a better system? And I thought for a couple of weeks, and I said, yeah, I could write them a better system. You know, it's simply conformity, make sure everything's conformed to a particular standard, accessibility, and reduce the amount of human intervention, really what everybody wants. So I thought, well, and since they're global, anyway, and so many subsystems all have to communicate, I said, yeah, I can run a better system, but can I give them the system that they actually need? And after 3 or 4 weeks, I said, no, I can't. Not with the same technology that the 3 previous attempts were done in. I said, there's no way I can create the actual system that they need. So I started thinking, well, what kind of system do we actually need? And so that's and so for 10 years, I've looked at just that problem. So I'm going to discuss that a little bit in this introduction to what Jane is. The problem is 99% of what we do in software development is human-based. It relies on our knowledge of everything, and so I'm trying to remove the human from the equation and have a system that simply performs actions. Computers only perform actions. All this AI and big data, basically you're asking the computer to perform an action. In software development, we have basically 5 or 6 actions that we can actually perform, which is our binary representation actions, which is add, subtract, multiply, divide, compare, shift, invert, and that's pretty much it. Move. Okay, so 5 or 6 or 7 instructions. So all of our compilers are identical. That's all they do. They don't do any more. Our flow control is terrible in our applications. Our dependency on what we do in software development is dependent upon talent and experience, and that should not be. So I'm trying to build a system that removes the human from the equation. So I have a list of 11 basically changes to the fundamental technology, which is, first thing is change the binary representation of numbers. Computers only work with numbers, or a set of bits that we think of as numbers. So these bits, this set of bits represents a number from 0 to 256 or something. The permutations that we can have in 8 bits and so on. And I want to change that to a binary. Right now it's all fixed. We can pick a number of bits. What if it could be variable length? So if we go to variable length and all these variations of versions, we have 3 versions of our GPS now because they didn't pick enough bits, and so on and so on. We have IPs, we had 4, now we have 6, and next year it's going to be 8, and so we're going to have to keep changing all of our variations of our software. And our assemblers are horrible. Basically they're trying to accommodate, be backward compatible back to the 8080 on all their versions, and it is I know about 12 assemblers and it's a nightmare. And our compilers only do these, you know. Whether you write in a so-called high level language, I don't consider them very high level, if all they do is these 8 instructions. That's it. You can add, subtract, multiply, divide, compare, and that's about it. You can't do anything else. It doesn't remember anything. It knows nothing about anything. We put everything in our source code. Anyway, so the first thing we want to do is change, and the binary, if we change the binary representations to variable length, then we don't have to worry about how many bits, and that simplifies our opcodes, because then we could add a 3-bit and an 8-bit number, and the hardware could do that. Then we wouldn't have to worry about all these declarations that we're doing, which is killing our technology and slowing it down. It slows it down quite a bit. Okay. Next, we want to change the way we draw characters on the screen. We have 1868 technology for our text that we program in. Basically, our 1868, 3 years after the Civil War, our typewriter was built, and that's pretty much our technology for developing applications. Okay. Next, how we store information. Here we have files and folders, so we stick them in a bucket. We don't know what that bucket contains. We rely on the human to determine what's in those buckets, and then we hard code that into the source code, which is the wrong place for it completely. So, I mean, what we're relying on is every individual on the planet now has to understand what's in that particular file, and if they need to get access to it, that's their responsibility, because that information is put in the source code. So we get it out of our source code, we take as much of this human knowledge that we represent. Oh, well, that's a 4-byte integer, or that's a 7-bit color, or whatever our technology is hard-coded in our application. So we have things like Word and Excel and, you know, find the cat in a picture and all of these applications, but they're all very specific to a given application. The data is not shareable, so we want to get to where we can share it. Anyway. So the next thing is, how do we access information? So right now it's all hard-coded into our programs, how we access that information, and that makes it proprietary, and that makes it impossible. And then when we program, where the human has 5 minutes when he understands how to access information, you know, is that information really, you know, anyway, so it's the access of information. Basically, it comes down to where we put it, who knows where we put it, and what we call it. And our naming conventions is not a technology, I'm sorry. Okay? And we want to change our computer languages that we use. Our computer languages, like I say, wouldn't matter if you wrote in Lisp or APL or Assembler or Fortran or Cobalt or C or C Sharp or any of these languages, they're all identical. And actually, it's not the language that we're programming. Our logic is all based upon these functions that are collections that somebody else wrote to push us into a design. So we're not designing anymore. We are simply trying to figure out what somebody else did in, let's say, the C++ compiler. How did they move that value from point A to point B? Do they, you know, I was writing VB the other day, and because I just wanted a simple little form, and I said, I want an array. And it says, well, we don't support arrays anymore. You have to use object. And I'm saying, you know, it's been 3 or 4 or 5 years since I used VB, and it's like, you know, things keep being changed on us, and we have to get to a point where we have no incompatibilities over time, which is critical because we have to move forward. Okay. And then we need to allow access to source code, meaning that if I can't see the source code that somebody put on my hardware, then I have no idea what they're doing. They could be, who knows what they're doing, and this is part of security. So if I'm a bank, I'd like to know exactly what's being run on my system. You know, our TVs, what are they doing? Are they taking pictures? We don't know, you know. And then we need access and control. Absolutely. We bought some hardware. I'd like absolute access and control of the hardware. So if the company goes out of business or something, or I said, we got to get rid of device drivers. That's the first thing we have to do. And then we need complete access to the information that we create. We created this map. I need complete access to it. And with complete access, then I'm 100% confident that it's the best that it can be. I'm running my company. I'm doing cadastral mapping, which is parcel mapping or tax maps. You know, how much tax do you pay on your property? And that's a very important thing. And I would like to make sure that that's being done properly. And the logic. We also want complete control of our logic. What is actually being performed? We're treating logic as something special. It's not. It should be just like information. It's just the way that we perform an action. It's not, so it's just more information. Turn this screw, move that lever, lift your left foot up, whatever. Those are just simply actions, which is information, and so that should be treated at the same level that all of our information is. Okay, this is a 4-byte integer. Fine, that's information that I know, but I don't need to know that. The computer needs to know that. And so that's what we're trying to get to. And then we need absolute secure information and logic. They say we can't do this. We can't do this in our current technology. No, I understand that. That's simple. But we can get to absolute information at the information level, at the logic level, and at the hardware level. At the hardware level, it's a little harder, but I think we can do that. And we need hardware independence so that we work to build these applications. We work to make things beneficial to the world. Then the logic doesn't change. The hardware is doing the same thing. You know, it may calculate the sine or cosine differently. I know once I was doing, USGS published their projection algorithms, UTM state plane and so on, in Fortran and in C. And then they produced a sample sheet of conversions of all the projections in a 1-degree grid across the globe. And so I took that and I said, okay, I wrote these in Fortran, let me run those. And I took C and ran those. C I did first, and the test. So when I did the conversion in my program, I wanted to make absolutely sure it was the same as USGS. So it matched up 100%. Went to Fortran, same algorithm, same company wrote these, and there was a difference. There was a 1-bit difference. And so what I'm saying here is we need to know absolutely that it's hardware and software independent, and it was different. And so I had to go in and change the last bit, 64 bits or whatever. I had to change the very last bit because it was being toggled, but it then became impossible to make comparisons, and so I had to get them identical. Anyway, these are the things that we as software developers have to do, but once we solve these, it should be universal. Okay, and then we need application independent information, meaning that, you know, we're sticking it in our, here's the information, here's the DLL, what's the structure of it? And we can do this. I did this. I'll demonstrate this when I get Jane out there, which is that our data structures are not limited to just what we know. So we need to put our knowledge into the data structure itself. Putting it in your source code is wrong. Basically, that means your source code, and you can't read your source code. Well, exactly what happens in it. So we need to put that information directly in the data so that we're no longer dependent upon versions, because we constantly change things. But if this particular, so if you're running a company and you have 10-year-old data and you've added 10 fields and took out 4, it shouldn't make any difference, because that data says, look, these are the fields we have, this is the format, this is the logic, you know, this is how we calculated the logic, these are the numbers that represent the maker or the manufacturer, and all that information has to be stored with the information that we're sending around. That way we can completely share this with anybody. So if we're sharing between England and the US, we say, look, they're always on meters. We need to get units in there so that information's in there as meters, and we come back to a standard system of inches and feet and things, then that all gets converted for us, and that's the logic we want to get to. Okay, and then a single infinitely large application is what we're after, meaning that when I started, I looked at the internet and I said, the internet is an infinitely large document. I love that. Okay, we used a simple little A tag that says, look, we can get to any page in the world by this name, these strings that we put in here, and we can get to any page and pull it up as though it were just the same document, which is great. But it doesn't really work, because we can't trust that string is going to be consistent. We tried for about 10 years to share links and, you know, and use this. We have so many broken links now, just about every page you go out there has broken links on it. And that's simply because we cannot control what somebody else does. And so in an infinitely large application, we have to realize that. It can only be one. We can't have any 2 people make a decision. And so that's kind of the basis for Jane. We need to get the human out of the equation and get everything out of our source code that doesn't belong there, so that we can have a cumulative software. These are some of we want to remove the client-server technology, basically have the system do all this, act like the world is one machine, one namespace, one memory space. These are the things that we need to get to, because we're leaving it up to the human. If we take that out and we just have one namespace, then it's kind of like an infinite large application now. So we talk about the mouse, my mouse, your mouse, somebody else's mouse. It's all in a name, right? And so it's no longer, you don't have to worry about access or the logic necessary to retrieve it or to store it. And so we want to move there. And compile in style means that we'd like to get, right now our technology is, like I said, 1868. typewriter technology, one-dimensional fonts, which is terrible. We need to get two-dimensional fonts, and so that way we could edit and program in style. Means we could determine that color means something, or that underlining, or that we create dynamic fonts so that the user can say this is A prime, and A prime is a single character, not two characters. So yeah. Anyway, there's a whole lot of technology that we're looking at to remove and move forward. Right now we're stuck in a terrible technology that doesn't work. We'll remove the need for documentation, remove the concept of versions so that everything is forward and backward compatible. Simply the way we look at the world. We want to be able to program in our historical handwritten style, which is mathematics. You know, this is an integral and lambda and the three dots for the therefore and so on. We know that technology is 1,000 years old. We built that technology to work. And with a computer, we could really make it very, very convenient for people. And we want access to all binary information. So usually we have one namespace. So that's just part of our namespace. So we say, let's say a DLL or something, or how many sections is it? And so it's just part of our namespace. We want 100% confidence in our information and our technology. Right now I have none. We blow up rockets, and this is simple doing it. It's not the talent, it's simply our technology that we don't have the information we need to do our job properly. We need understandable logic. It means that right now we're right. I took a course at Georgia Tech and probabilities, and I'd say, okay, great, there's a probability, and we typed it in, and we did add, subtract, multiply, loops, but I could not tell you if that code, what that code did. I could not tell you that loop and that particular add, subtract, and compare was a probability. We were doing land classification kind of technologies, and I couldn't tell you what that code did. Somebody could tell me that that's what it did, but reading the code, I could not tell you what that, and I wrote it. I said, okay, what exactly, you know, are we doing here? So we need a technology that supports change. And we're constantly changing things. And that's why I'm saying we can't have versions. Look, it's changed. I added, you know, a new graphic type. You know, we have all kinds of curves. You know, we have, if we want to add something, we just add it. And it's 4 lines of code, literally, that we're adding. But it gives us new capabilities, and we're constantly changing them. We want to take something out, take it out. It doesn't exist. The thing says, look, it doesn't exist. You can't do what you want to do in that particular data because it doesn't exist. Fine. We can deal with that. And then finally, we want the right to repair, right to access. I bought the hardware. It's mine. I'm sorry. It doesn't belong to you anymore. I need complete access to it. I need to repair it. These people are stealing your information, stealing your hardware, and I think that's wrong. But that's me. I don't care. You say, well, it can't be done. I'm going to do it. And finally, all of this, if I get it done properly, I can't get it done, not in my lifetime, but maybe I can move it forward. Finally, all this would put me out of a job, because if we do this and then software is accumulative, means that there is an end to this sooner or later, maybe in 50 years, maybe in 100, maybe in 200 years, but at least we can move toward a pretty much completion. It'll never be done, but who cares? But we're not going to get there with the crap that we have now. Our technology doesn't work, no matter what we think of it. And this AI bullshit, it's just another application that is using the same technology. If we get out of technology, yeah, I don't see anything wrong with doing natural language processing. Here's a command. I could not tell you how I walk. Oh, well, we'll just make it natural language. Up to a point. But so much of what we do, we don't even understand what we do. How does our heart beat? How does our brain work? How do we walk? How do I tell people to go to the store? Us, we really just want to say, go to the store and get me a loaf of bread. I don't want to tell you all the inner workings of that. And that's what I'm hoping to have this completed, hopefully in a month or two. I keep saying that every year, but I keep finding that our technology needs to be completely redone. I started with a compiler. I changed, I took JavaScript and wrote the compiler, got it to do, I did all kinds of things, and then basically I polished it. I changed the flow control, which is terrible, and our namespace and our, just all the technologies that don't exist. I put units in there, fractions, and all kinds of things in there, and after 3 or 4, that's why it's taken so long. After 3 or 4 years, and I had 800 to 1,200 changes, just fundamental changes to JavaScript, to our technology, whether it was C or C++ or whatever, it's still the same thing. I found it was just polish on a turd. It didn't really change the technology. So in conclusion, what we're really after is one system, one computer language that covers all environments. So the language will accept mathematics that we write on paper, music, chemistry, formulas, physics, geometry, Word documents, word problems, and all of our existing scripts that we now use. They should be able to accept those. They're just languages, very trivial languages, but they are languages. All of our function calls are just a language. Here's the name of the function that I want, here's the name of the action I want you to do, sort, and here are the parameters that I'm going to send you. Now it's all shoot from the hip type of programming, but that's what function calls are. It's a syntax. The first one has a name, and that corresponds to whatever name you have in the function that you called it, which isn't very consistent, but that's our technology. Thousands of languages, millions of languages. If you call every function call a separate language, which in actuality it is. We have computer languages, which do our adds, subtracts, multiplies, and divides, and compares. But we also have the languages of our DOS commands is a language. JCL was a language. Job control language. Deck control language. These are all languages. All of our shell scripts in Unix are languages that all perform actions. DOS runs programs. JCL does batch processing, and so on and so on. These are all languages, and we should have one language that will accept them all. There's no reason we can't. And so what we don't realize is that we're forcing the programmer to learn all these different languages for all these different environments that don't interact. So when we have our source code. We'll take a very simple example. We have our source code, okay, and it has, it generates let's say an executable or an emulator or whatever, but that's not our program. We have programs that build those. Well, these 3 files go together to build our output file. So we now have a make. I don't like that, but this is our make files, which is a separate environment just to build our programs. And then we have the program itself that determines what actions are going to be performed. So those are separate actions, which should actually be one action. And then we have, how do we install it? Where do we put it so that we can run it? Is it dynamic? Is it static? And so we have thousands of these subsystems. Now we said, we don't really have client-server technology, so we'll create something called a script called Python that says we'll just send that program over and we'll run it over there. Anyway, we have a lot of these things that all of these separate technologies that we have separate languages for, and we need one. And it should be absolute to be able to handle anything with a lot more power than we have now. So that's what we're after, is one environment. So third grader uses the same environment as the chemist or the pharmacist or the doctor or the airplane pilot. They're all the same system. And once we do this, then all of this inconsistency that we have in our current development system, which relies on humans to do all this work, which is, there's no reason. Anyway, so we will move forward and get into a better environment and basically put me out of a job. And then I think what we can do is then if you want to do research, you want to build new algorithms, then you eliminate 99% of the work you're doing now, which is you're learning how to be a programmer. How do I get that value over here, and how do I add these two values, and how do I do how does the sign function work, and that's what you're working on. You're not working on the logic that you're an expert at. If you're making medical equipment, you're more interested in how the heart works than you are on how to get that image on the screen. That's what we should be after. Not this trivialities of simple logic with no units. We don't have units on any of our programs. We don't have any function. We don't have anything hardly. We have add, subtracts, multiplies, and divides. That's my system to consolidate all this into one universal language, powerful language, not the triviality that we have in our current compilers, which is almost nothing, mathematics, so that when we do a probability, we can look at it and that's a probability equation. Then we're communicating to the human exactly what logic is being performed instead of us converting our logic into trivial hardware operations of add, subtract, multiply, and divide, which means nothing to us. Hopefully I'll get Jane out fairly soon. All the pieces are there. I just have to put them together. Running across things that fail to do in our environment. We've been working on this for 250 years. We've been in computer science. And you said, well, wait, Cliff, we started in 43 or 36, I think, with Zusa and his Z computer. But we had Babbage back in the 1840s or so. But we had, prior to that, we had human computers. And then before that, in 1776, we had Adam Smith, Wealth of Nations, which is kind of my starting point for computer science, which he said break it up into opcodes. And so for 250 years since 1776, we've been doing exactly that. We broke it up into opcodes of add, subtract, multiply, divide, and compare. Babbage then used that to build his computers. The Baron used that to get his human computer simplified so that he could hire high school kids to do the math opcodes and somebody else to do multiplication opcodes and somebody else to do division opcodes. And that way he did not have to have experts in a complex formula, and he could simplify it, which is what we did with our computers. And we haven't gone any further. We don't have units, we have no consistency, and so that's where I'm at. I'll leave it here, and hopefully we can get this out so you can actually see it. It's a lot more powerful than my little explain. I'm trying not to explain all the details because there is quite a bit to it. Anyway, well, thank you for your time, and hopefully we'll see you in the future. Bye now.